you're going to hear me talk about latches and flip-flops. The flip-flop is what we primarily use in the design of our sequential circuits. A latch is easier to describe when you're first constructing it. A latch is what we call transparent. That means that if the clock signal is high, any change on the input is immediately propagated through to the thing that you store, which means if the input changes a lot, the output will also change, and that can be a problem because if those changes somehow loop back, as you'll see we sometimes do, that can cause feedback loops and weird stuff. So that's a little bit unstable. It's very easy to design. As we have done, those devices that we've designed are called latches, and if the clock is 1, any change gets propagated through, and so that means that the state can change multiple times when the clock is high, which could be a problem. A flip-flop is called event-triggered. That means that the change happens only when the clock changes. The value is stored only when the clock changes, not while it's high or not while it's low, but when it transitions from high to low. This takes a bit more work to develop. It's not that hard to do. Usually it's done by putting a latch and then another latch right behind it, and then the value is stored from the first latch into the second latch. I'm not going to walk through those designs. You can look them up in textbooks. It's worth understanding. But basically the difference is edge-triggered versus level-triggered. So a level-triggered device, like a latch, will change as long as the clock is open. Most of our clocks are open when they're 1, so when the clock is high, its value can change a bunch. A edge-triggered device, or an event-triggered device, will store its new value only when the clock transitions. And for most of what we do, it's when it transitions from high to low. As it makes the transition, it stores a new value, and because that transition happens on a single event, on an edge, rather than the duration of the high clock value, that means we prevent these sort of feedback loops and other things. It allows the rest of the circuit to stabilize before the next state is stored. And you can see more details about this in the book and in a few other places. But starting now, I will usually talk about flip-flops instead of latches, just because that's the devices we actually end up using in our machines. And so a D flip-flop then, just like we talked about a D latch, it will be changed on the clock edge instead of the clock level. And as we designed, the next state is always going to be equal to the input regardless of the current state. It will hold its state if the clock is disabled. Now with a flip-flop, that is while the clock is high or while the clock is low, it will hold its current state and allow that state to be used in the rest of the circuit. And then it will transition only when the clock changes, and usually only in one directional change. So the output is not going to change until the falling clock edge causes the device to store a new value.